Hello, so I've been given this really quite funky looking curve and this quite disgusting looking equation here. And I've been told that each of the points, P and Q, the tangent to the curve is parallel to the y-axis. So what does that actually mean? Okay, so here's the y-axis. Okay, so if the tangents to the curve at P, so over here and over here, are parallel to the y-axis, they're basically just parallel to, they're just a vertical line pointing upwards. So at P, it looks something like that, okay, and at Q it looks something like that. Sorry, I can't draw straight lines very well on here, but that's basically what's going on there. So they're just a straight line going vertically upwards. And I've just been told to find the coordinates of P and Q. Now, if you're looking at that and if you're thinking, where on earth do I start with that? Okay, pull out some keywords. Right, so the diagram shows the curve of the equation. Well, that equation isn't going to help us at the moment. Okay, it's just kind of a bonkers equation. Can't do anything with that because you've got like x squareds and y cubes going on, and like the x's and y's are all mixed together. Ugh, it's disgusting. Don't even go there. Okay, but we have been told that each of the points P and Q, the tangent to the curve. That's about the only thing that I can really pull out there that's got any meaning and allows me to go forward with the question. Because if you think right back to C1, right back to the end of C1, when you first started learning about this thing called differentiation, you learnt that differentiation gave you the gradient function of a curve. So what that literally means is if you go around a curve and if you draw the gradient of that curve, so the gradient of the curve is just the tangent, okay? So differentiation, tangent, they kind of go hand in glove with each other, okay? They kind of mean the same thing. So when you differentiate, you're basically finding the gradient of the tangent, okay? So let's go with that. So I'm looking at tangents, so let's try differentiating. So I'm going to take this function here, x squared plus y cubed minus 8x minus 12y equals 4, okay, and I'm going to try and differentiate that. Well, I can't, can I? Because the x's and y's are all kind of mixed together, right? If I was given something like y equals 3x plus 4, I could definitely differentiate that because that's dy by dx equals, well, it's just 3 in that case. But here, the x's and y's are kind of mixed together, they're not separated. And actually, if you try and separate that out, you're just going to make a real mess. They're properly mixed in with each other. And we say that because they're mixed in with each other, and I can't write y on its own and then a bunch of stuff involving x on the other side, okay, because I can't write it like that, we say that that's an implicit function. So this up here is an implicit function because they're kind of mixed together. If I can write them separately, then we say it's explicit. So you've probably learned in your course, or I hope you've learned in this course, this thing called implicit differentiation, and that's why it deals with functions that you can't write explicitly. Okay, and the way which you do it is just basically the glorified chain rule. The way which you do it is you first of all start by writing d dx in front of everything. So let's just first of all understand what the notation d dx means. Let's take a value, just a random value x, okay, and just do a little quick thought experiment, okay, and I put it into a function. So this is my function, and I get y out. What that literally means, so a function is literally saying I take a value, I do something to that value, and I get another value out. Well, that's kind of what you do with differentiation, except you're not taking a value anymore, you're taking a function. So in other words, you take a random function, okay, you differentiate it, and you get the derivative of that function out. So you get another function out. So I'm going to write that as d dx because it behaves a bit like a function. It behaves a bit like a function in the sense that you're taking something, doing something to that value. So with a function, you're taking a value, doing something to that value, you get another value out. With differentiation, you take a function, you do something to that function, and you get another function out. So it behaves in the same way, but we don't call it a function anymore because otherwise we're saying we take a function, we apply a function to it, and we get a function out. Too many functions going on. We call it an operator instead, an operator, because operator just literally means the same kind of thing as a function. So the differential operator is d dx, okay, and the thing which we want to differentiate goes in here. It behaves exactly the same way as a function. So if you see this written down, that's literally what it means. So let's start off by writing d dx to differentiate every single thing, every single term. Just start off by writing d dx in front of everything. And trust me, write d dx in front of everything. I mean everything, okay? So that's d dx in front of that thing, 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 and then don't forget the 4 as well. So d dx in front of everything. I've literally just written d dx in front of every single term. You might try, for example, to differentiate that in your head. Don't. First step, trust me, because otherwise you'll make a mistake. Write d dx in front of everything, okay? Okay, so let's have a look at it. Now we've written d dx in front of everything, we can now look at see what we can differentiate, because I can see some stuff in there that I can differentiate. Like stuff just involving x, I can totally differentiate. So that's differentiate x squared. Well, that's just 2x, right? So I can totally do that bit. I'm going to leave that second bit there at the moment because it's stuff involving y, so I'll come back to that in just a second. I've got stuff just involving x there, so what's the derivative of 8x? That's just 8, okay? And again, stuff involving y, so I'm going to leave that alone for a second. And then look, I've just got the derivative of a constant, just derivative of 4, so that must just be 0, okay? So I've got stuff in there that I can immediately differentiate, okay? Now let's look at the stuff which I can't currently differentiate. So let's have a look first of all at this thing here. So in other words, d dx of 12y. Okay, now I'm just going to, like we do with integration, we can just pull a number out the front. So anything which is a number, as long as it's not like got y's or x's and stuff, if it's a number, and if you've been multiplied by that number, then you can pull that number out the front. So I'm just going to pull that 12 out the front. Okay, well, d dx of y, so this literally says differentiate y. Now you can think of this as just simply saying, when we differentiate y, it's just going to get dy by dx. Okay, you can think of it as a bit like a function. Okay, think about the chain rule, for example. We have like some function in here. Y is just like some function, so it could be like y equals x squared plus 3x plus 2, for example. How would you differentiate that? Well, you differentiate everything on the right-hand side. On the left-hand side, you differentiate this, and you get dy by dx. Okay, so you could write it like that, or you could think of it as like the function itself. So y is like properly a function, okay, and that function is just like to the power of 1, okay, so that basically that 1 sort of climbs down, okay, and then it just kind of becomes dy by dx, okay, so it just comes to be 12 dy by dx. That's all that literally just becomes. So that's 12 dy by dx, okay, that's nice and easy. Let's have a look at this then. So what is the derivative of y cubed? So again, this is a bit like our chain rule notation. If I had something like x plus 3, or 2x plus 3 to the power of 4, okay, then I differentiate that. That would then become, well, the 4 climbs down out the front. I leave the thing inside the brackets alone, and I reduce that power by 3. And then I multiply by the derivative of whatever's inside that brackets. So the derivative that's inside that bracket, that's 2 in that case, okay. So let's do the same thing here, okay, except here, my function in the middle, my 2x plus 3 is just basically a bit like y. So if I just put a couple of brackets around that. So I'm literally saying just try and differentiate that, the same thing as we did down here. Okay, so let's bring the power down first of all. So 3, leave the thing inside the brackets alone, so that's still y. Okay, and then I just reduce the power by 1, so that becomes 2. Then I multiply by the thing inside the brackets. So what is the derivative of y? Well, we've just shown up here that the derivative of y is just dy by dx. So that's just dy by dx. Okay, so that thing there, that whole thing there just becomes 3y squared times dy by dx. So let me just tidy this up now. So I'm literally just going to rewrite this out. So I've got 2x, that's my first term when I differentiate it. My second term when I differentiate it, just becomes 3y squared dy dx. Okay, my third term is then it's minus 8. Okay, my fourth term is minus 12 dy by dx. Okay, and then I've just got equals 0 over the right-hand side, okay? So I've just literally differentiated that thing. But remember, when you differentiate it, you want dy by dx equals stuff on the right-hand side, okay? So in other words, I need to just try and rearrange this, so I just get dy by dx on its own. So let's first of all start by taking everything which isn't dy by dx over the other side. So I can see I've got an 8, I can see I've got an 8 here, and a 2x here, or a minus 8 here, and then 2x here. So let's take the 8 over the other side. So I'm basically left with 3y squared dy by dx minus 12 dy by dx. So let's take the 8 over the other side, and let's take the 2x over the other side, so it becomes 8 minus 2x. That's all I've just done, just taken them over the other side, okay? So plus 8 and minus 2x. Okay, let's have a look at this then. I want dy by dx on its own. Well, can you see I've kind of got a dy by dx there and a dy by dx there. So let's factor out a dy by dx. So I've got dy by dx. Okay, and I've factored it out. What am I left with inside the brackets? Well, I've got 3y squared, okay, there, and then I've got a minus 12 there, okay, and that's all equal to 8 minus 2x. Okay, I just want dy by dx on its own. So I'm literally just treating like dy by dx just like another variable, just like factoring out a variable and then kind of rearranging it just to get that variable on its own. Okay, so I'm left with 8 minus 2x. Okay, let's divide by all of this thing. So 3y squared minus 12. Okay, so that is literally what dy by dx equals. So when I differentiate this horrible looking function, where is it again? This horrible looking function up here, okay, basically I end up with that. That is the derivative of that function there. And notice that the derivative even has x and y's mixed together. That's how to do implicit differentiation. Okay, so this is literally just what I've got here. I've got dy by dx is 8 minus 2x over 3y squared minus 12. Now let's just think, what have I found there? I found the gradient function, okay? I've found the function which would give me the gradient at any point on this curve. So if I knew this point down here, for example, so x equals, I don't know, x equals like 1, I don't know what that is, okay, I go up there, I stick it into this equation, okay, and then I can find what the gradient is going to be. So this is literally what I found there. Okay, but I've been asked to find what the points P and Q are. So do I know the gradient of the so I know the tangent is parallel to the y-axis, right? So do I know the gradient of the tangent? Well, yes, I do, because it's kind of the opposite of a stationary point. Are you happy that horizontal line, so I guess the stationary point will lie up here, a horizontal line is a stationary point, okay? And that is just where the gradient is 0. It's kind of like a change. It's not changing at all, okay? So remember that gradient is given by change in y over change in x, okay? Let's imagine I have a gradient like this, for example. Let's just say I've got a straight line like that, okay? I can then go, well, that's my change in x, that's my change in y, so that's my change in x, that's my change in y. Divide change in y by change in x, that'll give me my gradient, okay? Well, with this kind of situation, so with my vertical straight line, what is my change in x? So in other words, how far do I move across in that direction? What is my change in x? Well, are you happy? Because it's a vertical straight line, I'm not moving across by anything. It's just going to be literally a vertical straight line. It's literally like I'm not moving across by anything. It's got no gradient, effectively. So my change in x is 0. It doesn't matter. It doesn't matter what my change in y is, like blah, 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 whatever that is, okay? Whatever I change by y, it doesn't matter because I'm dividing by 0, okay? And whenever I divide by 0, that comes out as infinity. Well, it's positive or negative infinity. We don't know whether it's infinity upwards or infinity downwards, but it's infinity, okay? So basically, a gradient of a straight line which is vertical is infinity. So here, dy by dx is infinity, and the same thing over here. Okay, I'm just sticking plus or minus in there because if you're a pure mathematician, you'll be shouting at me if I don't. Okay, so it's positive or minus, positive or negative infinity. So gradient of a horizontal line, that's a stationary point. The gradient is 0. Fine, we know that. But gradient of a vertical line, the gradient must be 0. The gradient must be infinity. Okay, so if the gradient is infinity at this point, so I know this must be infinity, don't know what that means, must mean that I'm dividing by 0, because this literally means this going on here. So vertical line means the change in x, how far I move across, okay, must be 0. So in other words, that denominator there, that 3y squared minus 12 must be 0. And then just a case of solving that. So I get 3y squared equals 12, okay, fine. And then I just divide through by 3, I guess. So I get y squared equals 4, okay? And then I get y. Well, just be careful when you take the square root, because this is literally saying like some number squared and I get 4. Well, you happy it could be 2, but it could also be negative 2 as well. But actually in this case, it doesn't matter too much, because remember that's my y coordinate. Okay, so it's either positive or negative 2. Well, you can clearly see, because it's above the x-axis, it must be positive 2. Okay, so if you forgot about that, don't worry about taking the, if you've got to take the negative square root as well, don't worry about that, because the negative square root, so negative 2, corresponds to also a point down here, where you've also got a tangent which is vertical, so you'll also have a tangent which is infinity down here, but we're not interested in that, we're just interested in the case when y is positive 2. But remember, look, we've been asked to find the coordinates of P and Q. So we know the y coordinate is 2 of P and Q, but we want to find the x coordinate. Well, we've got an equation which links x and y together. It's literally this thing which we're giving up here. It's horrible, but we're giving it up here. So all we have to do is just sub y equals 2 into that, and we'll find out what x is. So let's just go for it. Whenever I see a y, I'm going to put 2. So x squared, I haven't got a y, so I just leave it as x squared, plus y cubed. So that's just 2 cubed. I see a y, I'll replace it with 2, minus 8x, no y's there, minus 12 times 2. I'm going to put it in brackets, just means 12 times 2, and that equals 4. Okay, cool. And then I just expand that out, and I just have to find what x is. So I've got x squared plus, what's 2 cubed? That is 8, isn't it? Plus 8 minus 8x. what is 12 times 2? So that's minus 24, isn't it? Minus 24 equals 4. Let's take everything which isn't an x over the other side. So I've got x squared minus 8x equals, I've got 4. Then I add, wait a minute, that's a quadratic. Do you know what? I've changed my mind. I'm going to take everything onto the left-hand side, so I've just got equals 0 on the right-hand side, because that's a quadratic, and I can solve it if it's equal to 0. Okay, so I've got 8 minus 24. So minus 24 plus 8, that's minus 16. Okay, then I take the 4 over the other side, that's minus 20. Okay, then I just hope, fingers crossed, that I can factorise this, and I think I can. It's 10 and 2. So I've got x minus, sorry, that's negative 10 x plus 2, okay, equals 0. So I get two coordinates. I've got x equals 10 and x equals negative 2. So my two coordinates are x equals negative 2, that's clearly going to be over here, that's the negative one, and x equals 10, that's clearly going to be here. So the coordinates of P, let's just go up here a little bit more. So I know the coordinates of P are negative 2, 2, and I know the coordinates of Q then are 10, 2. A lot of work there, but it's just basically implicit differentiation and then just sticking stuff in formulas. Easy.